Hello friends. Today in this session we'll see some examples from completeness chapter from matrix spaces by Pawan Kumar Jain and Khalil Ahmed. Few examples are related with constant sequence, eventually constant sequence, and then other are related with convergent Cauchy sequences. So firstly, we'll see what is meant by constant sequence, eventually constant sequence. So what is a constant sequence? A sequence xn n equal to 1 to infinity in metric space xd is constant if xn is equal to x for all n. If all terms of that sequence are same, then that sequence is called as constant sequence. Eventually constant sequence is nothing but a sequence whose all terms are same after some n. Okay, a sequence xn n equal to 1 to infinity is eventually constant if there exists positive integer n naught such that xn is equal to x for every n greater equal n naught. After some n naught, all terms of that sequence are same. Constant sequence is always eventually constant, but eventually constant sequence need not be constant. Now we prove that every constant sequence or eventually constant sequence is convergent sequence and hence Cauchy sequence. Okay, so example, so that any eventually constant sequence in metric space xd is convergent and hence Cauchy, because we know that every convergent sequence is Cauchy. So solution, let xn be eventually constant sequence. In matrix space xd. What this implies is there exists some positive integer n naught such that xn is equal to x for every n greater equal n naught. Then for given epsilon greater than 0, there exists n naught, positive integer n naught, such that d of xnx is equal to d of xx is equal to 0 less than epsilon for any n greater equal n naught by 1. This implies limit n tends to infinity of xn is equal to x, and therefore xn is convergent. And converges to x. Hence result. Or thus every eventually constant sequence is convergent. Okay. Constant sequence must be convergent because xn is equal to x for all n from first term x. That type of sequence is known as constant sequence. So for n naught is equal to 1, d of x and x is equal to d of xx is 0 less than epsilon, whatever choice of epsilon may be. Means that n naught is equal to 1 works there. And in this case, after which n naught all terms are same, that n naught work for eventual constant sequence. Okay. Now, in discrete metric space, we'll prove that every Cauchy sequence is eventually constant. Next example, let XD be discrete metric space, XD be discrete metric space such that d of xy is 0 if x is equal to y and it is 1 if x is not equal to y. Then any Cauchy sequence xn, Cauchy or convergent, in x is eventually constant. Solution. So let xn be every eventually constant sequence is convergent or Cauchy, no problem. Okay. Let xn be Cauchy sequence in discrete metric space. Cauchy sequence in discrete metric space XD. Therefore, for epsilon is equal to half greater than 0, there exists some positive integer n naught such that d of xn x naught or xn xm is less than half for any m greater or equal n naught. In particular, d of xn naught is less than half for any n greater or equal n naught. And therefore, d of xn naught must be 0 for any n greater or equal n naught. By definition of D, distance between 2 points is 0 or 1. So as it is less than half, therefore distance between xn and xn naught must be 0. This implies is xn is equal to xn naught or every n greater or equal n naught. Okay, and therefore xn is eventually constant sequence. Thus, every Cauchy sequence, because we are taking arbitrary Cauchy sequence. Every Cauchy sequence in discrete metric space is eventually constant. If it is convergent sequence and it converges to x, then this xm just get replaced by x. Again xn will become x for every n greater or equal n naught on same line. Okay, so we can easily prove that every convergent sequence in discrete metric space is also eventually constant, or in previous lecture I think it may be proved. Okay, now we'll take next example. Let Y be subspace of metric space XD. Let Y be subspace of metric space XD. Let Xn be sequence of convergent sequence in YD subspace. Means it is sequence of points in Y such that limit of Xn is equal to X. Then limit of Xn is equal to, then should add X belongs to X. So what is given here? So here Xn is convergent sequence of points in YD such that limit n tends to infinity of Xn is equal to X belongs to Y. Okay. This is subset of X. Then by uniqueness of limit of sequence, convergent sequence, limit n tends to infinity of Xn must be equal to X belongs to X. So this limit cannot change. Because if that sequence is convergent, it has unique limit. Next example. Let Y be subspace of metric space XD and Xn is sequence of points in Y such that limit n tends to infinity of Xn is equal to X belongs to X. So Xn is sequence of points from Y only, but its limit point lies in X. Then Xn is Cauchy sequence in Y. Okay. Solution. Every convergent sequence is Cauchy. Okay. So for this, d of Xn Xm is less equal to d of Xn X plus d of X Xm 1. Now since limit of Xn is equal to X belongs to X implies for sequence Xn in YD. Therefore, for given epsilon greater than 0, there exists positive integer n0 such that d of Xn X is less than epsilon by 2 for any n greater equal n naught. Using 2 in 1, we get d of xn xm is less than epsilon by 2 plus epsilon by 2 is equal to epsilon for any mn greater equal n naught. 2 in 1 and by symmetry of d we have. So d of x xm is same as d of xmx, right? So this is less than epsilon. This implies is okay. Thus, for given epsilon greater than 0, there exists positive integer n naught such that d of xn xm is less than epsilon for any m greater equal n naught. This implies is xn is Cauchy sequence in YD. So whenever we have some convergent sequence of points, if a sequence xn of points in Y whose limit lies in whole metric space X, that limit point of that sequence may not be nx, but that sequence must be Cauchy sequence in Y. Okay. So that we proved here. Next example. So let D and D star be equivalent matrix for set X such that say d of xy k1 times d of xy is less than equal to d star xy is less equal to k2 times d of xy for some fixed k1 k2 greater than 0 and any xy belongs to x. Then 1 xn is Cauchy sequence in xd if and only xn is convergent Cauchy sequence in xd star. xn is Cauchy sequence in xd if and only xn is convergent sequence in xd star. Second, xn is convergent sequence. Sorry, xn is Cauchy here. Convergent sequence in xd if and only xn is convergent sequence in xd star. So solution 1. Suppose xn is Cauchy sequence in xd. First, let xn be Cauchy sequence in xd. Then for given epsilon greater than 0, then so this is 1. Then for given epsilon greater than 0, there exists positive integer n naught such that d of xn xm, I want your d star of xn xm is less than epsilon, and d star of xy is less equal k2 times d of xy. So by using one, I have to cancel that k2. So here I'll take epsilon by k2. Okay. For any nm greater or equal n naught. From 1, d star of xn m1, or from 1, that is hypothesis. This is less equal k2 times d of xn xm. This must be less than k2 into epsilon by k2 is equal to epsilon for any nm greater or equal n naught. Okay, by 2. This implies xn is Cauchy sequence in xd star. We'll get it is to be Cauchy sequence. On same line, we can prove its reverse part. Okay. Now let xn be Cauchy sequence in xd star. Then again for epsilon greater than 0, there is d star of xn xm less than epsilon. I'll take k1 epsilon. Instead of epsilon, I am taking k1 epsilon now for nm greater or equal n naught. Nm greater or equal n naught. Okay. So d star of xn xm is less than k1 epsilon. Then from 1 again, d star of xn d of xy. Okay, d of xn xm is less equal 1 upon k1 d of xn xm, which is nothing but 1 upon k1 into k1 epsilon. For nm greater or equal this k1 get cancelled. Okay, by 3. I'll give 3 for this. Okay, here again from 1 and hypothesis will get this, and therefore xn is Cauchy sequence in xd. Xn is Cauchy sequence in xd. Okay. Now, if I assume that for second xn is convergent sequence in xd. Is it clear? For second, suppose xn is convergent sequence in xd such that limit n tends to infinity of xn is equal to x. N tends to infinity of xn is equal to x. Then for given epsilon greater than 0, there exists opposite or n naught belongs to n such that d of xn x is less than epsilon upon k2. For n greater or equal n naught. Then this is 4. Then by 1, that is hypothesis, d star of x and x, this must be less equal k2 times d of x and x, and it is nothing but k less than k2 into epsilon upon k2 is equal to epsilon for any n greater equal n naught by 4. This implies limit n tends to infinity of xn is equal to x belongs to xd star. xd star. Is it clear? Again, is it clear? Now I am just making some changes here. Again, suppose xn is convergent sequence in xd star such that limit of xn is equal to x belongs to xd star. Okay, then for given epsilon greater than 0, here I'll get k1 epsilon d star. Then by 1, d of x and x is nothing but d of xn, this is k1 d of xn x, 1 upon k1 d star of x and x from 1. And then we'll get this to be 1 upon k1 into k1 epsilon. This k1 get cancelled, and therefore d of xn is equal to x in xd. Okay. Thus result is proved. So with this discussion, we'll stop today's session here. Thanks for listening session carefully. Bye bye.